104, Summer Session 1, Final Project. Chapter 8, Gases, by Shanice Brown
and Desiree Hamilton.
Properties of gases. Gases are particles that are far apart and move fast. They are described by the physical properties of pressure, the force exerted by a gas against the walls of the container, volume, the space occupied by a gas, temperature, the determining factor of the kinetic energy and rate of motion of gas particles, and amount, the quantity of gas present in a container. An example of the properties of gas are: a sample of neon gas has a pressure of 0.50 atm. Calculate the pressure in millimeters of mercury of the neon. We already know that 1 atm equals to 760 millimeters of mercury, and they can both be written in two conversion factors, one being 760 millimeters of mercury over 1 atm, or 1 atm over 760 millimeters of mercury. 0.50 atm is our given, so we take that and multiply it by this conversion factor. 0.5 atm times 760 millimeters of mercury divided by 1 atm equals out to 380 millimeters of mercury. Boyle's law. P1 times V1 equals P2 times V2. Boyle's law determines the final pressure or volume when the temperature and amount of gas are constant. Volume changes inversely with pressure if there is no change in the temperature and amount of gas. Pressure increases if volume decreases, and pressure decreases if volume increases. An example of how Boyle's law works is: oxygen gas is delivered through a face mask during oxygen therapy. The gauge on a 12-liter tank of compressed oxygen reads 3,800 millimeters of mercury. How many liters would this same gas occupy at a pressure of 0.75 atm when temperature and amount of gas do not change? Our given variables: P1 equals 3,800 millimeters of mercury, and P2 equals 570 millimeters of mercury. We have converted both of these to atm. V1 equals 12 liters, so we must find V2. We rearrange our equation so that we get V2 equals V1 times P1 over P2. Here's how we write our equation. V2 equals 12 liters times 3,800 millimeters of mercury divided by 570 millimeters of mercury equals 80 millimeters of mercury. Or V2 equals 12 liters times 5 atm divided by 0.75 atm also equals 80. Charles' law. The equation for Charles' law is expressed as V1 divided by T1 equals V2 divided by T2. Charles' law determines the final temperature or volume when the pressure and the amount of gas are constant. Volume directly relates to temperature. When temperature increases, volume increases, and when temperature decreases, volume decreases as well. Here's a problem showing how Charles' law works. A sample of argon has a volume of 5.40 liters and a temperature of 15 degrees Celsius. What is the final volume in liters of the gas if the temperature has been increased to 42 degrees Celsius at constant pressure and amount of gas? These are our given. You must first convert all temperatures to Kelvin when dealing with gases. So 15 degrees Celsius converts to 288 Kelvin, and 48 degrees Celsius converts to 315 Kelvin. V1 is 5.40 liters, so we are looking for V2. Our equation changes from V1 divided by T1 times T2 equals to V2. So V2 equals V1 times T2 divided by T1. Here's how we solve our problem. V2 equals our given, which is 5.4 liters, times T2, which is 315 Kelvin, divided by T1, 288 Kelvin. Kelvin will cancel out, giving us our final answer of 5.91 liters. Gay-Lussac's law. P1 divided by T1 equals P2 divided by T2. Gay-Lussac's law determines the final temperature or pressure when the volume and amount of gas are constant. Pressure directly relates to temperature. So when T increases, P increases. And when T decreases, P decreases as well. An example of Gay-Lussac's law is an aerosol containers can be dangerous if they are heated because they can explode. Suppose a container of hairspray with a pressure of 4.0 atm at room temperature of 25 degrees Celsius is thrown into a fire. If the temperature of the gas inside the aerosol can reaches 402 degrees Celsius, what will be its pressure in the atmospheres? Here's our given. Again, we must convert the degrees in Celsius to Kelvin. T1 will convert to 298 Kelvin. T2 will convert to 675 Kelvin. Our P1 is 4.0 atm, so we are looking for P2. We change around our equation to equal to P2 equals P1 times T2 over T1. Here's how we solve our problem. P2 equals our given 4.0 atm times T2, 675 Kelvin, divided by T1, 298 Kelvin, which Kelvin cancels out. You divide these two and you multiply by atm, which gives you 9.1 atm as your final answer. Combined gas law. The equation is expressed as P1 times V1 divided by T1 equals P2 times V2 divided by T2. The combined gas law calculates the final pressure, volume, or temperature of a gas when changes in two properties occur and the amount of gas is constant. It is the relationship of pressure, volume, temperature, and moles. It determines the effective changes in two variables on the third. Here's an example. A 25 milliliter bubble is released from a diver's air tank at a pressure of 4 atm and a temperature of 11 degrees Celsius. What is the volume in millimeters of the bubble when it reaches the ocean surface, where the pressure is 1 atm and the temperature is 18 degrees Celsius? Assume the amount of gas in the bubble does not change. These are our givens. Convert your degrees Celsius to Kelvin. So T1 equals 284 Kelvin, T2 291 Kelvin. P1 is 4 atm, P2 is 1 atm, V1 is 25 milliliters, so we must find V2. We change around our equation so that V2 equals V1 times P1 divided by P2 times T2 divided by T1. Here's how we solve this problem. V2 equals 25 milliliters times P1, which is 4 ATM, divided by P2, which is 1 ATM, times 291 Kelvin, which is T2, divided by T1, 284 Kelvin. ATM and Kelvin both cancel out. Once we finish our calculations, we are left with 102 milliliters. This is known as a double. V1 divided by N1 equals V2 divided by N2. Avogadro's law calculates the amount or volume of a gas when the pressure and temperature are constant. Volume directly relates to moles. When N increases, V increases. When N decreases, V decreases. Here's an example of Avogadro's law. A weather balloon with volume of 44 liters is filled with 2 moles of helium. What is the final volume in liters if 3.0 moles of helium gas are added to give a total of 5.0 moles of helium gas if the pressure and temperature do not change? Our given values are V1 equals 44 liters, N1 equals 2 moles, N2 equals 5 moles. We know when N increases, V increases, so we must find V2. We change around our equation so that V2 equals V1 times N2 divided by N1. To solve this problem, V2 must equal to 44 liters times N2, which is 5 moles, divided by N1, which is 2 moles. Moles will cancel out, and after doing the math, our final answer is 110 liters. Law. The equation is P total equals P1 plus P2 plus P3. Dalton law calculates the total pressure of a mixture of gases. It is the sum of the partial pressures of individual gases. Partial pressures equal the pressures exerted in if it were the only gases in the container. Here's an example. A heliox-breathing mixture of oxygen and helium is prepared for a scuba diver who is going to descend 200 feet below the ocean surface. At that depth, the diver breathes a gas mixture that has a total pressure of 7 atm. If the partial pressures of the oxygen in the tank at that depth is 1140 millimeters of mercury, what is the partial pressure in atm of the helium in the breathing mixture? Our equation tells us that P total equals PO2 plus PHE. P helium equals the P total minus P oxide. P oxide must be converted to atm, so we take 1140 millimeters of mercury and multiply it by 1 atm divided by 760 millimeters of mercury to get 1.5 atm. Because this is now our new equation, all we have to do is subtract 7 atm minus 1.5 atm equals to 5.5 atm. The end. Thanks for watching.